Today's paper is called Gated Attention. Oh, sorry, I just lost the paper. Okay, this is embarrassing.
It's called Gated Attention Networks for Learning on Large and Spatio-temporal Graphs. Yeah,
sorry about that. Yeah, it's a bit of a mouthful. So yeah, it's Gated Attention Networks, and it's still in line with this attention-based models that we've been doing for a while now. It actually draws some inspiration from transformers, but in the particular case of graphs. And leading the discussion is going to be Dan, who is a data scientist at NPlan and found this very interesting paper. Go for it.
Cool. Thanks, Carlos. So yeah, as Carlos said, I'm going to be presenting this paper about gated attention networks for graphs. So it follows on quite nicely from what Amin presented last week, and sort of adds a little bit on top. So yeah, let's just get started. Right. So hopefully you guys can all see that. Yeah, cool. So yeah, as with last week's paper, this paper is seeking to address problems that can be expressed using a graph. You know, some measure of connectivity between examples, and it mainly focuses on trying to label nodes. Yeah.
Sorry, if you can zoom in the screen, I think.
Oh, absolutely, yeah.
So it occupies the whole. Thank
you. So yeah, as I was saying, they introduced the problem by saying there are many problems in the world that involve a graph structure, involve some network between examples. And similar to last week as well, they're saying that convolutions are an idea that we could maybe use to try to exploit the graph structure, but we need to think about how the right way to define a convolution in a graph case, what the right way to define a convolution in the case of a graph is. You know, it's easy to define a convolution with an image because you've got this regular structure. What do you do when you have a more irregular structure that nodes might not have as many neighbors as each other? It's not immediately obvious what that aggregation ought to be. So the thing that they propose here is a type of aggregation, and yeah, they just introduce at the start the fact that they're calling this graph convolution a graph aggregator. So I think that's worth mentioning first, and then I'm going to jump down a little bit to this diagram here, so we can think a bit more about the steps that they've gone through or thought about with graph aggregators to come to the novel part of this paper. So on the right, you can sort of see some quite simple aggregators that aggregate something about the neighborhood of the nodes to get information about this central node. So in red, you've got the central node, and then these are the neighbors, and we want to aggregate the information somehow. So all this pooling aggregator is doing is somehow putting together the feature vectors of each of the neighboring nodes into one aggregated node vector. And similarly with pairwise sum, it's where are we? So it's just a little bit further down actually. We're just summing up these some weighted function of the feature vector of the node across all of the nodes in the neighborhood. So these two are types of aggregator that are quite simple, and there are some learned weights, but here there's no learned weights at all, for example. So what we talked about last week is this one on the left, the attention aggregator. And so that introduces a linear operation and a nonlinear unit to add between the, oh, I don't know what's going on here, sorry. Can you hear me all right?
Yep.
Okay, cool. I just got a message saying that my audio quality might be affected, but hopefully not. Let me know if it is. So on the left here is what we were talking about last week. So these weights are learned using a fairly standard idea of attention, as we talked about in a lot of previous weeks. And we use that possibly with multi-heads to get some different representations of the nodes. And these representations are then used to generate a final encoding of the node. And that encoding is what's used to then classify it or cluster it, whatever it is you want to do. So the novel part of this paper is, and so this is what's proposed in this paper, and the novel part is here. And the way that they describe, so what this is a vector of scalars across the heads of the attention mechanism. And these scalars basically tell you for your particular combination of node and neighbor, how much attention should you pay to that particular head. So perhaps in a situation where one of your heads is encoding something about a very connected node, maybe it doesn't make sense to include that representation in an encoding of a not very connected node. At least that's the intuition that they go for, right? So let me just find where it says it.
Daniel, can I ask you a question about that? So that,
please,
that makes intuitive sense. And as I was reading it, the question that came to mind is, it appears to be a general point about multi-headed attention that's not actually specific to this setting. And so, I didn't see anything in the paper where they said, and you could use gated attention, generally speaking. And so that made me wonder, A, is anyone else using a kind of gated or masked attention in that way? And secondly, if not, does the problem that they're, claiming to be addressing with the gated attention, is that something that people feel is showing up in other settings?
That's a good question. I'll be honest, I'm not sure. And it's sort of something that I was thinking about myself. Obviously we're thinking about something about the nodes in the neighborhood and how they relate to the center node anyway. Are we not encoding something about how much attention we should pay to a particular head?
Yeah. So
go ahead, Carlo.
Oh yeah. So it's a bit of an interesting question because so they're not using self-attention, right? They're using a more traditional type of attention where you have your query is your key is your central node, and then your query and values are the surrounding nodes. So it's a more traditional view of attention rather than self-attention. And if you go just a little bit down to how they define the weights at the attention weights, there is you can see that there is a learnable parameter there, right? And the only learnable thing is that it depends on the neighborhood. So that I don't think it's showing in the screen, Dan.
Sorry.
Anyway, equation 3, yeah. Yeah, so only the central term in equation 3 has learnable weights, those theta m parameters. So I would say that something like this is very much suited to a graph because it seems to be saying, okay, set the weights depending on the context. I'm not sure how it would generalize to other things. I guess you could do something similar for images and so on, but I would expect self-attention to take care of that on its own.
So
good. Thanks, Carlos. That actually makes sense. And I wasn't thinking enough about the difference between self-attention and kind of non-self-attention attention mechanisms.
So Carlos, what would you say the distinctive difference between self-attention and non-self-attention? Like, we're paying attention to different parts of the graph. Is that not self-attention in a way?
Not quite. So in self-attention, the whole sequence is the input, and the sequence is learning how to make attention with itself. So everything is connected. So you learn weights of all the possible connections between the different elements of the sequence. So if you were to, whereas here, so that in self-attention, the keys, the queries, and the values are both taken from the whole sequence. Here, your keys are taken from one place, and your queries and your values are sorry, it's the other way around. Your queries are taken from X.
Your queries.
Well, I get I get confused, but anyway, your queries are taken from one, and then your keys and your values are taken from the context. So you need to somehow include a representation that says, okay, this is how you will learn from the context. Whereas when you do self-attention, the whole thing is coming into the mechanism, so you can expect it to learn which representations are important, and then you have several different heads which learn different representations. So this part is sort of taken care of at the expense of exploding parameters. Like what's interesting here is that they get away with very few parameters, and they achieve something like what self-attention is trying to achieve as well.
So would it be feasible to, I mean, computation no object, would it be feasible to do something like self-attention on a whole graph? Is that it, like, theoretically?
I'm not sure whether the difference for attention is that attention has a variable number of parameter of objects measured against. And I think for graphs that is important, right? Because your graph structure does vary from node to node, where self-attention sort of assumes that the structure you put in is always the same number of items in your sequences. So, and I think that's where attention is just more generalizable.
Yeah, that's true. Yeah, in self-attention, they rely on like padding to say that something is in there. With respect to generalizing self-attention to graphs, I would expect it's quite tricky. It's like with images, right? You need to define the sequence in a clever way. Nothing comes to mind, but I can't imagine feeding a whole graph into a self-attention into a transformer, for example. It would be quite huge.
Yes. Global properties or something.
Okay. So, yeah, hopefully that was clarifying at least a little bit. Yeah, but because we're not using something like self-attention, we need to include these gate parameters that basically learn which head to pay attention to, given the structure around the node in question. Okay. And so I think now that we've sort of gone through at a high level what's going on. Oh. Okay. Adam's saying he's going back and reading self-attention, which is a good idea, I think. I might do the same. So yeah, I think having gone through all of that from quite a high level, it's maybe useful to go through at least a little bit some of the equations they're putting in. Now, I spoke to Carlos earlier, and we both felt that they've maybe gone in a bit too much depth with notation here, but I think it's worth just like visiting what they think or how they define a multi-head attention aggregator. So the difference between what they do here and what last week's paper did is they use different parameters to get keys and query vectors. So these are key and query vectors, basically. Don't think there was any real need to talk about them in a fully connected layer type notation, but all this is a key and a query vector. And then we take the softmax across those to get these weight values, the attention weights. So pretty standard. And then we use our value vector, which is this, and concatenate. This operation is just concatenation with our original feature vector, and then use a fully connected layer at the end. And so we can see that here. We're taking the dot product here with our so like you say, Carlos, I can't remember which way around it is, but one of these is key and one of these is query.
So the queries, the queries come from your central node. So the node that you're trying to make a prediction on, that's your query.
Yeah.
Your keys and values come from the surrounding. So you do one mapping to get the keys. So query gets multiplied with keys, and then it gets so that gets transformed, gives you your attention weights, and then you attend on the values, and that gives you your attention map.
So I hope people can see the flow through here. We've got two examples, one on the left, one on the right. We take the dot products, and then we take the softmax, and then we combine that with our value vectors to get our attention head outputs. And the difference here is that we then apply, so the gated attention aggregator is just the same thing, but we include these attention weight parameters, the gate weight parameters at the final stage before we concatenate everything together. So that, we're paying attention to the right head, basically. Cool. So I think that basically tells us what the aggregator is.
I have a bit of a comment here. It's a bit of a point of discussion here. So I don't have an answer to it, but so it seemed to me when I saw the diagram up there that so the learn gates, it's what the transformer is trying to do with concatenating the attention heads and then doing the linear mapping with learnable weights. I think it's a bit similar, except it depends directly. It depends directly on the keys and queries. So the gates depend on the queries and the keys. But I don't know. I'm not sure what. Like I said, I'm not sure if this is something graph specific or if it can be generalized a bit more to just to deal with other attention mechanisms.
I mean, their implementation doesn't feel particularly graph specific. All they're doing is, so yeah, maybe it's worth going into that now. To get, yeah, like you say, they're not really doing anything particularly complicated here, right? It's just a fully connected layer on all of the neighbors of the node in question, and then max pooling, right? So
yeah, that is the other question, because they call it a convolution, but then they just do pooling. So I don't understand. I didn't understand that. So they said, yeah, they said that these gated weights, they're created with a convolution layer, and then they put the equation. It's just a max pooling layer. So
that doesn't look right.
I mean, maybe it's convolutional because the weights are shared. So it's, I don't know, what does everyone think? Can we call this a convolution, or?
I suppose so, in that you're combining elements of like a wider structure into one element, right? One scalar, and then learning something about that.
Yeah, I think they're stretching it a bit, but
yeah.
But yeah, I guess that central term does look like a convolution in a way that you're sharing weights across all the realizations of your across all the examples, right? So anyway, it's I don't know, it's weird.
Bit of a stretch, yeah, I'll give you that. Okay, cool. Any further questions about this bit? Yeah.
So this is not exactly about it technically, but it's just, this is highlighting to me a thing that I'm also less sure about with multi-headed attention. Basically, what if anything, is there anything that drives the different attention heads to differentiate other than initialization?
That's a good question, and one that I don't immediately know the answer to. Carlos, do you know? How do they end up capturing different representation?
Yeah, so it's tricky. I don't think there's anything, there's nothing in the architecture necessarily forcing the attention heads to learn different representations, other than if learning different representations helps improve on the target, then the network will learn different representations for each head. But there's nothing specific forcing it. So I guess there could be a case where several heads learn similar representations. There was a good paper. There was this paper about that was saying that that transformers were learning convolutions, and there you could see, so that they had these interesting graphs about the learned weights of each of the attention heads, and you could see that some of them were similar. So yeah, there's nothing in particular forcing them to learn different representations.
So I remember that was a. Have you seen has anybody else seen other papers that have looked into the differentiation in across attention heads?
So
something
I personally haven't. Yeah.
No.
I think so. I know that in some of the image processing, in some of the image, in some of the computer vision papers that we have presented, they do show sort of like the intermediate weights and so on. So you might be able to get something from there. I personally don't think it's very interesting to analyze the different representations that the heads learn. And this is like, I guess other than intellectual curiosity, I don't find it very useful, because in the end, what you want to do is combine all those representations meaningfully to for your classification target. So what the individual heads are learning sort of becomes a bit irrelevant in the grander scheme of things.
The only thing that I can think of that is sort of like adjacent to this is that, like, frequently these papers do ablation studies on how many heads they need, right? And usually it's actually not that many. So maybe adding more heads is just adding complexity and not really, you're not getting any new representations. That's just I have nothing to base that on really, but.
Yeah, I think also given the last week's paper, I think it was where they average or sum over the heads, right? Where you know that when you sum over them, the individual contributions probably are not that distinct. That it might be more of an ensembling step rather than a like enriching the complexity of the model itself. I'm not sure about that at all.
If you're just linearly combining them at the end, then do you need, how much difference do you need, I suppose, is the question.
Yeah, if one model gets overturned by the contributions of all the other, one head gets overturned, the contribution of all the other heads, then it doesn't matter what representation it has learned, right?
Yeah, I guess that's also part of the benefit of what they are doing here is, I guess, that if you have two redundant heads, the network will eventually learn that only one of them is important. So I would expect that G to zero out eventually. So that could be an interesting introspection tool to see how the model is learning. Just a thought.
Interesting. Cool. Okay, so I think that basically covers the theory side of things. There was, so after this, they go into talking about the models that they run and the experiments that they run. So the first one is an inductive node classification experiment. So you've got a graph and you've got some labels in that graph. And the experiment is to use those labels to train and then predict on some nodes of the same graph and see what your performance in that subset is. So they start by elucidating the structure of the model. And they say they stack these graph aggregators together to build the model, basically. Now, this paragraph, I sort of didn't really, I struggled to understand the relevance of this paragraph. I don't really know what they're sampling the node batches for. And I don't know if anyone has any light to shed on it. Like, was it?
I'm afraid, Daniel, I had noted the side of, I noted the margin of that one paragraph, and I was hoping that you would explain it to me.
Okay. Yeah, I don't know. Is this? Are there concepts that are similar to this in last week's paper? I can't remember.
So it's, sorry, I'm trying to get the, what page is it? 5.1. Yeah. Yeah, I think they're just saying how they propagate through the network, right? Because you have all the different layers. Yeah.
So this is training. At training, that they sample a mini batch, and then the next batch following that is some neighborhood of the nodes that were in the first batch.
Yep.
Yeah. Okay.
Yep. Just it's just sort of to say how the information propagates through the different layers. Because I don't know if you realize that they have a different number. So each layer needs to know the neighborhood to calculate the weights.
Yeah.
But the neighborhood itself is a fixed size, but you can have different number of nodes. So I think they define it as the minimum between the number of the, so the minimum between a hyperparameter and the number of neighbors. So if you want to do it randomly for each layer, you have to resample the neighborhood. Does that make sense?
If you want to do it randomly for each layer, if you want to, sorry.
So each layer uses a new random subset of neighboring nodes.
To calculate something about the neighborhood of the node in question.
Yep.
Okay. Okay. And so are we doing this because we need to know the representations of the neighborhood as well?
So they're doing this because they're not using the whole graph to learn. So what they said before in the training is that they only get a random set of nodes, because otherwise it's untractable, both in memory and time. So what they are doing is well, you start with a sample of nodes, whatever that mini batch is, and then you recursively sample from the neighbors of each of those nodes to get your M sampling steps.
Right.
So I guess it's a bit confusing because I don't know. I told you before that their notation is quite confusing, but they're using M layers and then they take M samples from the M layers. So it's the same number of sampling steps as they have layers. And then and then the aggregation is in reverse order.
You aggregate all of the nodes in BM.
Yeah.
Down to B0.
Yeah, I guess it's just to reduce the number of operations that you need to do. Otherwise, you're repeating so otherwise when you're aggregating the last one, you have to aggregate everything in between or something similar.
I guess it's like you need to know everything about the neighborhoods of the nodes you're trying to train on, right? So if you select a mini batch of B0, then you have to take steps out into the wider graph so that you know what you're going to aggregate. So you can get your representations for those nodes.
Yep. Yeah, I think so.
Okay.
Yeah, I think that about covers it. Yeah, again, because you have for the whole graph, you have a single training step. You somehow have to make it efficient so that you can get all the intermediate aggregations and so on. So then you can pass it on to your classifier.
Does that help, Adam?
Yes, that almost makes sense. I have a feeling that someone could write a really crisp, clean, simple version of this paragraph that would be obvious to anyone who read it. I think they're not actually doing anything very complicated there, but they're not defining their terms very well, and they're using slightly odd notation. And I didn't see anything in this paper suggesting that the neighborhood was a fixed size. But that was one of my questions. Was it a fixed size, or was it a fixed size with some sort of padding, or what?
I think they don't pad.
So
they do, which is harder as well. So what were you going to say, Carlos?
Yeah, so they don't sample from the whole neighborhood. So just in the paragraph above, they say that they at every sampling step, they only get either the whole neighborhood or a maximum SL, and SL is a hyperparameter. So SL just tells them, okay, if you have 20 neighbors, just grab 5, but if you have 2 neighbors, grab the 2 of them.
Mm-hmm.
Again, I like all of this. I don't suspect it helps training. I just suspect it's just to make the problem tractable and computationally efficient.
Yeah, I think this is it. They say that they need a way to step from the nodes they've sampled out into the graph. So a naive method might be to sample everything, but it's not practical on large graphs, exactly like Carlos just said. So they sample a subset depending on whether, like you say, the node has a neighborhood that's larger than this hyperparameter or smaller. Cool. And yeah, so that's the setup of the model. I think I understand a little better about what's going on here now. So hopefully other people feel the same way. And then they move on from there to discuss the 2 inductive classification setups experiments they did. So it's this PPI data set, which is proteins and their interactions, and the Reddit data set, which is Reddit. And yeah, there's specifics of what parameters they set here as well, which I won't go into, but we can basically move on to the results, I think. And they're comparing their network with the gated filters, with attention only, and with these more naive graph aggregators, and also just with a network that doesn't contain any connectivity information, just a naive neural network. And we can see that their gated attention network is performing the best. Yeah, it obviously is not a huge increase over the more naive aggregation methods, but it is obviously the best. And we can, yeah, we can see that actually one interesting thing is for the Reddit set, the 4-headed version is like, it's better than the 8-headed version. So maybe, yeah, a hypothesis might be that these 8 heads are encoding redundant information somehow, or not adding more heads is not adding any more useful representations.
Yeah. Go for it.
So Varhan's asked, is the Reddit dataset one large graph or many graphs like PPI? That's a good question. I think it's several graphs, but I'm not sure how many. So you mean the components that are disconnected in the PPI dataset? Is that what you mean? Yeah, I'm not sure, to be honest.
Thanks. Hi. I was just wondering, are they training on one graph and testing on another, or as you said at the beginning, do they train on all graphs, but using only part of the labels?
Yeah.
Reddit
I don't know.
it's one big
Yeah.
it's one big graph.
Is it one graph?
Yeah. So
they must just sample the nodes somehow.
Yeah, so
PPI
each node is a post and 2 nodes are connected if they are commented by the same user.
Right.
So you have a big network.
PPI is, I think, 24 or so graphs. I was just wondering how do they run the same experiment on different settings?
It's a good question. I guess you could.
Also, PPI is multi-class, right? So PPI labels, but each node can be in multiple classes. And Reddit, I see it in the graph. If you table 2,
yeah.
If you look table 2, it is multi-level, multi-class.
Sorry, is my screen not updating?
It updates slowly.
Now it does.
Okay.
Yeah, so they do say that for the multi-class they use a different activation function. So they use sigmoid for the multi-label and softmax for the multi-class. For the multi-class classification.
Yeah.
So the setup is a bit different, but otherwise they use the same algorithm.
If what you're asking is how they do the splitting, I'm not sure.
Yeah, initially I was asking about splitting, but then I also realized they can be very different. But that makes sense.
You don't need to split because you have labeled and unlabeled nodes in both data sets. So for the PPI, you can just run the algorithm for every graph and see once it's trained what labels it gives you for all of the unlabeled nodes.
Or if they are labeled, you just don't use the labels, right? It says here, if you look, this data set contains 24 subgraphs with 20 in the training set. Yeah. So that means they use 20 for training and the other 4 for testing. So they trained on some graphs and test on others. But for Reddit, they split to one graph. So that's important, right? Because then they are saying that their training can learn to predict on new graphs.
It's interesting.
Yeah, I mean, they're new graphs, but they are similar, right? They're
all molecules, but new molecules.
Yep.
Nice. Okay, thanks.
That are connected because they interact in a certain way. Yeah. I'm not sure, Vahan. I'm not sure why they've made this choice.
No, separate graphs are not connected, right? So they are individual graphs. There are no links between graphs.
Yeah.
I just want to
I'm not sure
that.
why they made this choice. But I guess Carlos is right. Like they've sampled some of the nodes for the Reddit dataset, and they're using those to train, and then testing on more nodes from the same graph. I imagine this Reddit dataset is one graph.
Yeah.
But I haven't read in this paper that it says that.
Yeah, it doesn't mention the. Oh, Reddit is an online discussion forum where each node represents. Yeah, it's just one graph.
Okay.
Yeah, cool. I think the point that Vahan made there is quite interesting, which is that you can predict on, you can use the same model to predict on new graphs. Like it's not just limited to learning in one graph and predicting in one graph, which is good.
I guess, they are similar graphs, but if your graph contains information that is similar to the one that you've trained on, then yes, you can predict on the new one.
Just like any other ML task, right? You can't train on images and predict music, right? It's the same thing, I guess.
Cool. So I think maybe it's worth talking about the PPI set here as well. you can see that it's performing extremely well for the 8-headed architecture. And maybe that has to do with the fact that they're sampling all of the nodes at each neighborhood step, right? Because the Reddit graph is so complex, you have to subsample by some amount at each neighborhood step, which means you're losing information, which means your accuracy is probably going to go down. And we can see that the accuracy on the left is lower than the accuracy on the right, right? But here, perhaps because we've got subgraphs, perhaps because we've got a simpler graph, it's feasible to sample everything. And so you're getting higher accuracy. I don't know, just a thought. Yeah, so like I say, they're talking about, yeah, there's an ablation study which is represented in this table that we sort of talked about, the number of heads and the sample size. Larger sample size means higher accuracy. And they also talk about the output dimension of the whole network structure. So in the PPI data set, they say the higher the output dimension, the higher this F1 score is. And we can see that it beats these other architectures across the board, and it gets better for the larger output dimensions.
And just maybe we can caveat that by it beats them by an extremely small amount.
That's a fair point.
Quite a few more.
Yeah, the parameter increase is what is it? It's quite large, really, isn't it? I
think, you know, on the one hand,
so
it's
like,
great that it meets them, but I you know, the beating is quite modest.
It's minimal, yeah. For the added computation, yeah, I would agree. It's not a triumph, is it?
It also, so there is I don't think there's added computation. You actually reduce the number of parameters. So if you go back to a table, if you look in PPI, you can see that actually the number of parameters for the 8-headed attention is reduced by about 80,000 parameters from pairwise.
Yeah, from
tonnage.
From these ones.
Yeah, for attention only. Yeah, not much, but it's also not that many more parameters, right? And when accuracy is that high, I guess you're all in the marginal gains territory.
It is. There's not much to be gained, really. But yeah, I see what you're saying. Still, that like Carla says, that these are all decreases from these more naive implementations that don't use attention. And I guess one last little bit, because we're probably not going to have time to talk about this bit, is this little plot here that shows the visualization of the 8-headed version for Reddit. So we can see for several different nodes that these gate parameters are quite different, and we're paying attention to different heads. Yeah, there's a variety of different weights across these 5 nodes. So we can see that they are having an effect, and we're changing where we're looking, dependent on the structure of the graph. Okay. And I will just briefly mention that this final section is about using graphs that also have a time element in them to build something that's a bit like a LSTM on the graph, or sorry, an RNN on the graph. And they use these graph aggregators to build or to design a new architecture that involves these graph aggregators to try and predict states of the nodes in the future. So I think it's kind of interesting, and it's it's tacked onto the end a little bit because they're basically not talking about their own graph aggregator. They're just talking about any graph aggregator with a time element in it. But it's interesting and worth a look if you end up having a look at this paper. Okay. Any questions?
I just wanted to make one last comment on that, on figure 3b, which I think it's a great figure, because what they're doing there is exactly what self-attention claims they can do, but with this massive attention mask, which is in a high level. They're saying, well, you have your node. So I don't know, let's say you have for some reason your keys, values, and queries, one of the features is color, or they're learning to represent color. So what they're saying is that, well, with this attention gate, what you're saying is, well, if this node is, if the query node is green and the node attended is red, then you should pay more attention to that node, or you shouldn't pay attention, or you should pay attention to color. But if the node is green and the other node is blue, then don't pay attention to color. So that's what these, or at least it's to my view, is what these gates are doing, which is also what self-attention does by including millions of parameters. So I think that's very interesting, and it's probably a good contribution of the paper.
Yeah, I hadn't thought about it in that way, but that is basically, that is what it's doing, right? It's like saying, if the neighboring nodes have these qualities, pay attention to them in a certain way. Yeah. Cool. Well, that was that paper. I thought it was pretty interesting. I hope other people found it interesting too. Yeah,
absolutely. So I guess that's it for today. Well, thank you very much, Dan, for the very interesting discussion. As usual, we enjoy working with graphs and attention. That is very much an area of research for NPLAN at the moment. However, we do want other people to say what are their areas of interest, and hopefully have discussions about it. So please do get in touch with us if you want to present a paper, or if there is or if there is a topic that you would like to talk about. I will be more than happy to accommodate. Otherwise, thanks, Dan, again very much. And that's it for this week.
Thank you very much.
Thank you, Dan.
Thanks, guys.
Thank you, Dan.
Thanks, Dan.